Good noon. Good noon. So it's my pleasure to introduce Amogh Sirnoorkar. Dr. Sirnoorkar is the Ross-Lynn Postdoctoral Research Scholar in STEM Education at Catalyst. I'm going to do his introduction, and I have an announcement. I forgot my announcement, but I'm going to get to it. He earned his PhD from the Department of Physics at Kansas State University in 2023. His current research and teaching focus on the integration of artificial intelligence in STEM education. At Purdue, he's received grants to support his work on students' engagement in scientific practices using generative artificial intelligence and developing an undergraduate degree concentration in applications of artificial intelligence in learning, science, and engineering. Amogh recently published an article in Computers in Education, Artificial Intelligence related to this presentation. He's going to be presenting a comparative examination of student and AI responses to a physics problem through the lens of sensemaking and mechanistic reasoning. And before I have you welcome him, can you advance the slide? Thank you. So my announcement is we have a slight change for our next Colloquium presentation. And I'll make sure I'll announce this very clearly through emails and so forth. But instead of on a Wednesday, it's actually going to be on a Thursday afternoon. It's going to be on Thursday, February 27th. And we have Dr. Lynn Ryan, who will be presenting about sustainability. Also, not only will it be on a different date, but it's going to be at the Discovery Learning Research. What is it called now?
Yeah, I think it's called the Hall of Discovery Learning Research.
Okay, the Hall of Discovery Learning Research in the afternoon on that day. And again, I'll send announcements so that it's really clear that change has been made.
And it's in conjunction with the Institute of Sustainability, I think it's called. Is it on there? No.
Okay. All right, so now please welcome Dr. Sirnoorkar.
So first of all, thank you so much for making your time for attending this talk. My name is Amogh, and I will be today, I'm a postdoctoral scholar at Catalyst, and I will be today talking about comparative examination of student and AI responses through the lens of sense making and mechanistic reasoning. So before diving into topic, so just let me set the expectations and objective of this talk and how this talk is going to proceed. So for the first 15 minutes, I'm going to broadly introduce myself as well as the research that I have been doing, which very well connects into this topic. So this is the sort of research and teaching that has been associated since the last 1.5 years that I have been here. So that I will be talking for the first 15 minutes. And then I will be talking, narrowing down and moving closer to the topic about what is the relation between AI and physics education. Simultaneously, I will be talking about generative AI, as well as how it is related in general with physics education. And then we will set up a research question and move towards theory and justify why that particular theory is important to answer the research question, which was further guided by motivation. And then we'll talk about methods. Then we'll speak about results and then conclusions. So this is along the expected lines. And lastly, we will have time for Q&A. So to be on the conservative side, I have in fact planned this talk for 50 to 55 minutes. But I estimate it to end relatively earlier to make time for talk. And I would also be perfectly fine if you have any pressing questions during the talk. I would rather prefer it to have a one-to-one interaction rather than all the questions being pushed at the end. So if you have any questions immediately as we move through the slides, feel free to go ahead with the questions. Okay. So let me introduce myself. As I mentioned, my name is Amogh and I'm a postdoctoral scholar at Catalyst. My research and teaching have both focused on applications of artificial intelligence in teaching and learning of STEM. I hold a PhD in physics education from Kansas State University, where my dissertation was focused on development and analysis of assessments that push students to make sense of physics using mathematical principles. So that's what sense making is about. And as you can see, there is a lot of focus on how students blend mathematics in making sense of physics. And then I have 3 years of teaching experience, both physics and interdisciplinary, and currently I am teaching these 2 courses this semester. I also taught one of these courses last spring. So these are all the background from which I will be talking today. Okay. So I will be just broadly outlining the nature of research that I have been doing in last 1.5 years and how it connects to the talk that I will be giving today. So there are 3 dimensions broadly that I describe about how I think about AI and how I proceed with investigation surrounding AI in education. The first one is learning about AI. So first, making sense of AI and understanding the strengths and limitations of AI platforms and AI responses in regards to STEM education, and this is broadly coming from my own experiences of being teacher as well as a student in STEM disciplines. The next one is learning with AI or learning using AI. So how do we leverage strategically AI in teaching and learning of physics and by extension STEM? So that's about learning with AI. And third one is preparing for AI. Now, given that we know what we know about AI, and from our own experiences of integrating AI in teaching and learning of STEM, how can we prepare students to effectively leverage AI for their own learning? And how can we equip educators to promote better learning experiences using AI? So those are the broad 3 themes. I'll just touch upon these 3 to go, and then we will dive into one of these in detail. So as I mentioned, I will be talking about this entire talk is focused on learning about AI. Just let me focus on learning with AI for a while. So one of the activities that I have been working on is to in fact promote analogical reasoning. So this is guided by an entirely different framework from UNESCO, and this activity was in fact guided by that framework. So I'll just briefly outline the nature of activities that we have been doing at Purdue. So in analogical reasoning, as you know, we often make sense of science using analogies, whether explaining electricity as a flow of water or motion of electrons as the plum pudding model that you have. So usually even scientists have explained the classical concepts using analogies. So the idea is that how can you facilitate personal analogies using AI platforms? So we did we have been doing activities in physics courses where we asked students to identify first some sort of idea or some sort of a concept which they find personally very difficult. So one of the things that we narrowed down was Morse potential. So that was a curve. So it's a Morse potential curve. So one thing that we asked students was to describe the curve in their own words and then push them to articulate or explain the same idea as if they would explain it to a second grader. The underlying idea was that, again, when you were to push students to explain a very complicated topic to a second grader, you are implicitly pushing them to create analogy. So first of all, they have to dumb it down, they have to create a story, and then they have to convey it. And we also asked students to pick a domain of choice, whether it be weightlifting or whether it be knitting or any activity that they like, and whether they can in fact articulate this whole concept in the domain of their choice. And we collected few other additional data. For example, did they find this whole activity easy and did they refer to any resources? And there are again implicit hypotheses that guide these questions. On the other hand, we also asked students to in fact refer to ChatGPT and ask the same questions. Like ask ChatGPT to generate the description of the curve, how it would explain to a second grader and how it would explain the domain of their choice. And we also collected these set of responses. And we asked students to compare and contrast. And we also ask students to find this whole useful. So we have a whole set of data that we are currently analyzing, in fact, using machine learning, like topic modeling and all, categorizing student-generated analogies vis-a-vis with respect to their understanding of the content. So there are some ideas that are going on. The next idea that we are currently working on is development of research-based assessments. One of the most powerful thing or a tool that AI gives in the hands of teachers is to customize and develop assessments based on your local learning needs. So what we did was we went into the literature of prompt engineering. We took all the prompting techniques and then we in fact developed a prompt template that would give you the research-based assessments that promoted scientific practices, that would engage students in scientific practice. So this in fact prompt template and all was guided by the 3-dimensional learning framework, which was pushed by NGSS a decade ago or so. So there is a lot of push on promoting practices, and it's very difficult to develop these assessments. So the idea was to develop a prompt template and see how can we develop customized research-based assessments. We are also developing coupled multiple response assessments in the same way. That's about assessments. So in fact, we submitted a grant. So we had a whole list of activities that we did in class, and then we had submitted a proposal which recently got funded from the Purdue Innovation Hub. And the last project that I'm currently working on is mapping the literature landscape of how people are using AI in physics education research. That is how in teaching and learning of physics. We are using Prisma framework, and we are currently working with current and past Purdue students on this project. Okay, so that was about learning with AI. Let me briefly talk about preparing for AI. We have been doing a lot of things in classrooms, and how can we in fact prepare future teachers, prospective teachers and students about effectively leveraging AI platforms. One thing that we did was we in fact wrote another grant for floating an undergraduate degree concentration program on the same, and we also have received funding, and this is in progress. And lastly, we also hosted a symposium almost last spring, wherein we had invited speaker from Khan Academy, Chief Learning Officer from Khan Academy, speaking about how do they develop AI platforms on their softwares, and students also presented their own experiences of interacting with AI and all. Okay, so that's actually broadly about the kind of research that I have been doing. Now let me dive into this learning about AI. Okay, so as we all know, generative AI has got a lot of traction. I mean, this is amongst all the stakeholders in education, whether it be policymakers, students, researchers, educators, parents. You name, almost everyone is nowadays talking about the role of AI or the potential role of AI in education. So fundamentally, these AI platforms are large language models which are generative in nature, meaning that it's a way in which you retrieve information. So the difference between a Google search and a large language model is that Google search in fact goes into its database and gives you the results. But the difference between a large language model is that it can generate something new from the existing patterns. It's not necessary that it has to retrieve the information, but it can also reconfigure the existing patterns and give you some new information. So that's why it is called as generative in nature, and it is pre-trained. It is being trained on billions of parameters, and that number is gradually increasing with new AI platforms now. And the last one is transformer. It is the architecture, or it is the vehicle that drives how these AI platforms. So these three things have been abbreviated as GPT. That's what you see in ChatGPT and all. So the earliest, the version that became in fact famous was 3.5, ChatGPT in 2022, November. And since then we have a lot of models coming out, 4.0 Turbo and 4.0 Mini and all. And these models have exhibited across all these models since 3.5. Almost all of them have exhibited very impressive capabilities. First one is human-like. So sometimes it's very difficult to distinguish between human-generated and AI-generated. So few people in fact even make that joke that the only difference that you can make is that AI-generated response is too good to be true. It's too perfect to be true. So that's how you distinguish. That's also a point that we are going to see. And it's very assertive in nature. So it's very difficult to test the inconsistency in AI responses. It's very confident, it is very assertive. And also it is multimodal, meaning that it's not just that you interact with text. You can have a voice input and get a video output. You can give imagery input and you can get audio output. So all the interactions are multimodal in nature. That's why there is a huge potential. People have argued that there's a huge potential for AI to transform STEM education, now particularly physics education. So this is where physics comes into play. Now for some very interesting reasons, physics has been one of the primary domain which has been used as a benchmark to speak about how good a particular AI platform is. So most of the times when GPT Turbo and all was introduced, so technicians and engineers used physics problems as examples to demonstrate how good their platforms are in responding to that. And there is a reason why that happens. First one is there is an active use of mathematics, a very rigorous use of mathematics in physics. And it goes not just in some parts, like sometimes the entire problems are pure mathematical arguments. And second thing is that you need both representational competence and representational fluency. So in physics, what you should do is you have to make two judgments simultaneously. You have to pick a right representation to express your idea. So the same idea can be expressed either in the form of a mathematical equation or words or a table of data or graph or anything. So one, you have to pick a right representation at that moment, and then you have to effectively navigate between multiple representations while solving a problem. That also we are going to see. So it is because of this complexity that reasoning becomes complicated sometimes, and that's why people have often used physics problems to demonstrate how good their AI platforms is. And moreover, whether it be use of mathematics or physics, they all are guided by first principles and laws. Even mathematics have their own first principles and physics have their own first principles, and anything that you do or anything how you solve a physics problem, they need to be guided by these overarching laws. So there is a lot of coherence argument that needs to be made within a physics problem. So that's why, not surprisingly, even physics education researchers have also been very hawkish on AI platforms. So the ChatGPT version 3.5, I think, was released somewhere in November, and we had a paper in December or January. So fundamentally taking an entire course assessment and giving to ChatGPT 3.5 and checking to what extent GPT 3.5 was responding, and it was done within first 1 month. And as you can see, there were a lot of assessment types, whether it be essays, end of chapter problems, programming task, multiple choice, clicker questions. Almost every form of assessment that goes into a typical physics course was entirely given to this LLM to check. And even with the most naive platform, people observed that it could just pass an introductory physics course. And it was, of course, even the first, the preliminary versions of AI platforms were almost acing standardized assessments. So standardized assessments are the assessments that are developed by researchers which take years of time and experience to develop them. And these platforms were just acing them. And now there are also ongoing investigations to check to what extent these vision capable chatbots are able to solve graphical problems. Now, as I know, AI models are now becoming multimodal. They can, in fact, read the, of course, see these graphs. So initially what used to happen was people used to prompt it explaining what the graph looks like, and the AI platform was to respond. Now they are in fact giving it and feeding the graphs itself. So they are also seeing very good impressive capabilities from vision capable chatbots. And whereas there are other studies too which have examined the role of prompting. Okay, now that not only that AI platforms are very good in solving physics problems, but you can in fact enhance their accuracy by strategically prompting them. So there is also research papers being published, and they are also investigating to what extent AI platforms are good at solving well-structured and ill-structured problems. So well-structured problems are the ones like that you find in typical end of your chapter questions, which have a clear starting point and end point. There is a clear answer and there is a clear path between the two. Ill-structured ones are the ones which they don't have. For example, if I wait to give an anomalous data of a system and ask you to generate a model, there is no right way of approaching this problem, or there is no one correct solution to it. So those are all called as ill-structured, and people are investigating them. They have also seen how to generate symmetric and context-rich problems. So there is a lot of research that goes with how AI platforms are faring on assessments. But one thing that in fact catches attention or that needs to be thought about is that there should be a need to go beyond gauging the accuracy or impressive capability of AI responses if we are thinking about bringing them to classrooms. Because one of the primary objectives of classrooms is often to promote or facilitate scientific inquiry or make students generate sophisticated explanations. So for that to happen, we need to in fact see how AI responses are exhibiting the features of scientific inquiry, how AI systems are unpacking or making sense of the given problem, and what impact it will have on students when students refer to those solutions. So with this motivation, the broad research question that I started exploring was, how do students and AI responses compare with each other with regards to the features of scientific inquiry? Now, if you have a group of students who solve a same physics problem, a very complicated physics problem, and if you wait to have the latest AI models give the same problem, what is the difference between how they approach and how they make sense of this problem? What are the inherent strengths and difficulties? Where do students struggle? And where exactly AI is pretty good at? And how can these efforts be complementary? So feel free to stop me if I am moving pretty fast. So this brings me to the whole idea of sense making. So sense making is the idea through which we make sense of how a particular phenomenon unfolds. It is through which we notice a particular gap in our understanding. Now, for example, as the screen went blank, immediately you started thinking about what was the reason why a screen went blank in the middle of a colloquium. That's true when the speaker is speaking it for the first time, right? So this is the process where you, in fact, you started making sense of what was happening, right? So what you did was you tried to bring in all your ideas that you have. There might be some problem with the power cord or power systems or the computer itself. And also some people might have observed that this fellow is unconventionally eased. So that means there might be a reason why it might have been intentionally done. So one thing that really happened was, for a moment, everybody was engaging in some sort of sense making. That is, you all noticed a gap between what was expected and what really happened. And it was a metacognitive activity that happened. And to address this gap, you started bringing ideas from your own lived experiences, and also your formal understanding about how systems work. And you also bring a lot of other unconventional ideas while trying to make sense of this phenomenon. And it's not just the bringing of ideas that happens, it's also establishing coherence between them. And finally, you generate an explanation that unpacks how a particular cause gives rise to a particular effect. So sense making is a very complex process that unpacks, and it is guided by this metacognitive reflection of noticing gap in your understanding. And if you wait to observe the last feature, which is mechanism, this unpacking a mechanism itself is a complicated process in itself, which is called as mechanistic reasoning. So this is one of the constructs which has been extensively studied in science education literature. So as noted, it is the way you unpack how a particular mechanism unravels. For example, this is one of the common activities that we do in science classrooms. That you take a metallic conductor, you heat its one end, and ask students what is the reason why you feel the temperature being going up on the other end, where it's not being heated. I mean, the common answer is that, okay, atoms are tightly packed in solids. As you supply energy to it, they start wiggling. And in this process of wiggling, they transfer the energy. And eventually that energy goes back to the last atom in the metallic conductor, and it also has the same sort of energy eventually. So what science education researchers did were, they proposed a particular framework about how do we gauge sophistication of mechanistic responses from students' end. Now that if you have a mechanistic response from students, how do you identify to what extent it is sophisticated? So the idea they proposed was some sort of 7 codes that you need to identify in the order of their increasing sophistication. So the idea was that the more sophisticated the code is, it subsumes the presence of the previous code. Now, for example, what is the target phenomenon? The target phenomenon is the process of feeling heat on the other end of the conductor. And what are the setup conditions? You know what are the setup conditions here, that the burner is on the one side of the conductor, whereas the other side is not being heated. And there are entities, for example, the atoms or molecules that wiggle that have vibrational energies, and you have activities that the entities engage in. So what are the sorts of activities? It's precisely the process of vibration or wiggling. And you have the properties of entities, that they are constrained by 2-dimensional or 3-dimensional motion, that they can only vibrate this way but not this way. And there are organization of entities and chaining. And the most important and the sophisticated code is chaining. That is, once you generate a mechanistic explanation, is your explanation enough to stand the test of various other arguments, or does it have a predictive power? Now, if you wait to generate any explanation, now let's say that if this burner was brought at the middle of this conductor, whether would your explanation hold good even at that point, or what would happen if it is on the other end of the conductor? So it's fundamentally finding the coherence, to what extent your explanation is powerful enough to make predictions. Okay, so now let me bring back. The objective was to check to what extent AI and student responses reflect the features of scientific inquiry. And we have 2 theoretical frameworks, and we have specific characters to look for in those responses. So one was these 4 features of sense making and these 7 features of mechanistic reasoning. So this was our theoretical idea. So what we did was, we took a framework called 3-dimensional learning assessment protocol. So we developed an assessment from real world context, wherein students were supposed to model a real world amusement ride context using formal mathematical ideas. So this problem was in fact constructed based on the prescriptive features of the framework. So this we call it as the gravitron task. I mean, I don't expect you to read the whole problem. Furthermore, what we did was we created two versions of it. One version was an open-ended version, and the other was scaffolded version where you had explicit scaffolds. For example, when you model a real-world context, you need to apply assumptions. You need to make a lot of assumptions. You need to idealize the systems, and you need to create a diagram to solve the problem and then do the math. So we asked it explicitly. Then, so this is how the problem looks like. I mean, I'm not going to present you the entire solution here, just to check like why we chose this problem to focus on. So this is actually a cylindrical amusement ride context where the rider leans against the wall and the cylinder starts spinning. So once it reaches a particular velocity, it pushes the person to the wall, and that person will be held in the middle, away from the floor. So the question was that given the parameters, whether that person would be falling down or not. So that was the primary question. So you need to construct free body diagram, you need to identify all the forces that are acting on that person, and then go back and do math, simplify the math, and you get an equation. You plug in the values and check whether this mathematical condition holds good or not. If it holds good, then the person is safe. Otherwise, the person is going to fall down. So there is a lot of things even at the introductory level that you need to engage with to solve this problem. So what we did was that we collected two sets of data. The first set of data was from students using Think Aloud protocol. So basically we gave these problems to students and asked them to think out loud, while simultaneously recording them through video and audio, and also simultaneously looking at the written solutions. So this was all the information that we collected. So practically what the student was writing, what the student was continuously saying out loud, and what was simultaneously the physical features or the gestures that the student was doing. So we had around 8 Think Aloud interviews for each of these problems, and there were two different sets. That means 8 for open-ended task and 8 for scaffolded version. And then we had this AI responses, particularly GPT 3.5, which was the earliest version that ChatGPT released, and 4.0 was at that point the most advanced version. So we also gave these two sets of problems using zero-shot approach. Zero-shot approach means without providing any context to the LLM. Provide the question the same way as you had provided to students. So we had particular features about how to identify these markers. For example, in noticing gap, how do people notice gap in their understanding, and what are the features that are visible when people do so? First thing is that iterative refinement of arguments. There are puzzling questions, and these are all backed by literature. So we have individual characteristic markers in this data about how to identify. So what we did was we analyzed case studies of individually of a student as well as an AI solution through the lens of these markers, and we also did qualitative analysis about what are the characteristic features or evidence of these markers in the two sets of solutions, and we also had an overall count, the quantitative distribution of these markers across the data sets. So I'll be just scanning through the results and we will be discussing them in detail. So these are the sample codes that I had from the two sets of responses. So the case study analysis was of a student named Joshua. It's a pseudonym. So one of the things that we observed was both data sets were equally representing the features of sense making. But however, one of the features that we observed from AI responses was the uncertainty in the arguments. It's not surprising because AI systems are very assertive. I mean, students often exhibit a degree of uncertainty when they make an argument. I mean, I'm not sure this is the right equation to use, but at least I will go with this equation now and see what turns out. So and so forth. So you can also categorically see a lot of uncertainty even coming up with different codes, but AI responses are pretty straightforward and confident. So that's one of the things that we observed. And across quantitative distribution, again, an interesting thing that we observed was the symmetric nature of AI responses. Almost all responses were evidencing the features of sense making, except for the feature of noticing gaps in understanding. There are two things. One, I mean, honestly, it's not very surprising. because AI platforms often mimic the responses from their training data, and most of the training data is from expert responses. So of course you have very clear arguments being put forth for a physics problem, and that's what they are evidencing. And that imperfection you see here, where students are exhibiting various degree of evidence for these markers. Now when it comes to mechanistic reasoning, this was something which was interesting that we observed. You can clearly see that the problem had right from the start, clearly articulating what is the target phenomenon that we are looking at, what are the initial setup conditions, what are all the relevant entities involved, and what are the activities that these entities are participating and all. Now these episodes, particularly the lower codes and higher codes, were not evidenced in student solutions. There are various reasons for it. Now, for example, when you are solving series of problems, you often take many things for granted. For example, when you are solving a problem, it is taken for granted that, okay, of course, this is the target phenomenon that we are addressing. But on the flip side, in physics, one of the most interesting things is to clearly identify the system. Like what is the target phenomenon, or what is the target system on which you are going to focus on, and then solve the problem. Like if you end up choosing an incorrect system, then you may not end up solving the physics problem itself. So that's why there is a lot of focus on system and surroundings in physics. So a good thing about AI response is that it clearly articulates everything. But however, students, when they are solving physics problems, by virtue of being tired or like just taking things for granted, they won't articulate everything. And this is also true for higher codes. It's not just that students, it's not that the AI solution just generated a solution. It backed up that solution by examining its predictive power. So that was also an interesting that we observed. And again, I would like to focus on these all 8s that you find from AI columns. So the AI responses are pretty good when it comes to evidencing the markers of mechanistic reasoning. And however, none of these solutions were conceptually correct. And one more interesting thing is the degree to which these AI platforms used diagrams to make arguments. The science education literature makes a very strong argument that mechanistic reasoning is closely intertwined with representations. If you are a science student, and if you are asked to explain how let's say a liver works, you either draw or you use gestures. So it is very intrinsically tied to how we learn science. But in terms of AI, because you have a ready-made solution just spitting out, even when it was not explicitly prompted, AI platforms hardly generated any representations, whereas almost every student generated a representation while making sense of it. So this was also more true, interestingly, in scaffolded version. Even when explicitly asked to generate representation, even the latest model, only half of the solutions generated representations. This we are going to discuss in depth, what its implications are for teaching and learning. So these are all the interesting things that we found. And again, there are a lot of imperfections from the students' end, particularly in open-ended tasks. They were not very explicit in highlighting these features of scientific inquiry, and there was always a degree of uncertainty there. So this is how a student solution looked like. So there were 3 problems. First, articulate what are all the assumptions that you need to make, then draw a diagram, and then work out the math and give us the answer. But because the problem was difficult, the student was saying out loud a lot of things and working out a lot on the rough sheet, but was unable to write anything concrete on the paper. But there were a lot of things that the student was doing right, which was not, of course, captured on the paper. And this is the solution just for the first problem that we had asked. What assumptions do you need to make from the AI platform? Even I was surprised that you can all make these assumptions while solving this problem. So it was very thorough when explicitly asked about assumptions. And this was the representation that it generated. I just want to show you, this is the representation that student generated while simultaneously highlighting all the forces. This is typically how it is taught in physics courses. It's not surprising. Even I would almost draw a similar diagram if I was solving this problem. Because when you are used to solving hundreds of these, drawing these diagrams, you usually draw this so that you understand what you are trying to do. GPT 3. This was the representation that GPT 3.5 generated, and this was the latest model, how it generated. This was also very interesting to us. Like, it was almost giving a three-dimensional picture of what was happening, including, like gravity, normal force, static friction, and even identifying the normal force and all. So it was pretty good.
Facing the wrong way though.
No, we will highlight this. In fact, there is an interesting point that I will come back to this diagram. Even the reviewer had noted the same point. Okay, so let's start discussing the results. The first thing that we observed was AI responses very elegantly reflected how science is talked about. That is, whenever you want to communicate an idea about how to solve a physics problem, you first identify what is the target system, what are all the relevant entities that are involved, how they interact, and then do the maths, get a result, interpret the result, back the result. Like this result would also hold true. So this is very intrinsically tied to how physics or science is talked about. And students' responses on the other end reflected how science is practiced. So when you start solving a physics problem, you first draw a diagram, try to make sense of it, use gestures, and then examine what is given, what is not given. So these are all the features of scientific inquiry about how science is practiced. So one thing that we observed that AI responses reflect how physics is talked about or how science is talked about. Student responses reflected how physics or science is practiced. Unlike students, AI's solutions evidence most features of sense-making and mechanistic reasoning. So, barring for few, mechanistic reasoning and sense-making features were almost perfect with AI responses. AI was particularly better at describing physical features of the system in light of conceptual ideas and evidencing higher and lower and higher codes of mechanistic reasoning. So this is in fact one of the biggest strengths of what I would call. One of the things that often students struggle is, if you were to give a real world context, what is the right physical quantity that is applicable or that is playing a role in that particular context. So this is something that students have a high degree of difficulty with. Now whether it is the normal force, whether it is the angular momentum or what. AI was pretty good in identifying what entities were involved in this given physical scenario and why other entities were not the right quantities to think about. And also, again, evidencing the lower and higher codes of mechanistic reasoning. Something which is often taken for granted, it was explicitly highlighting, and something which is not expected as part of solution, like to check the predictive power of a solution. AI response was consistently highlighting. Half of students' responses highlighted again. It was a good thing that almost 50% of the student responses consistently evidence some sort of uncertainty in their arguments, which was clearly evident with, I'm not sure that this is the right approach, but let's see. And once they picked an equation, they in fact at some point they just left it and picked another equation. So there is this whole process of trial and error to check what is the right approach to go for. And as we noted, one of the things interesting find was a huge wide degree of assumptions. The student just said that, okay, let's assume that the wall is perpendicular to the floor. And AI responses provided detailed assumption, at least 8 of these detailed assumptions of why these assumptions matter, what are these assumptions, and what would happen if these assumptions were violated. So actually, in fact, this is a very good practice about communicating science before you model a real world context. So students hardly referred to them when solving open-ended tasks. So if you remember, open-ended task had no explicit prompts to generate or to call out for assumptions. Students hardly generated when not asked to, and when explicitly prompted, they often struggled. So assumption is something that is often not practiced in classrooms. Even if you wait to ask students, assumptions is not something that they are very comfortable with. While scaffolding had no effect on AI solutions, student responses better evidence mechanistic reasoning with explicit prompting. So AI responses, it did not matter whether you explicitly asked or not. but it mattered a lot to students. So students in fact solved better when they were explicitly prompted few things. Among the AI solutions, there were no quantitative differences in evidencing the features of the two processes, whether you take GPT 3.5 or 4.0. In terms of evidencing or in terms of their ability to mimic their training data, there is no difference. Fundamentally, I mean, you can easily use even the free version of AI to unpack mechanistic reasoning processes in classrooms. However, none of GPT 3.5 solutions were accurate, and almost every response of 4.0 was correct. So there is also the conceptual accuracy divide between the earliest and the latest model. So the accuracy is, again, as noted, it's in fact increasing with every platform that is coming out. So with every GPT 3.5 generated a diagram when explicitly prompted, but that was not the case with GPT 4.0. Provided correct description. So this is something that I wanted to get back. So when you made a comment about the incorrect positioning of the rider inside the gravitron. So with GPT 4.0, what interestingly we found out was it provided the right representation about how to construct a diagram, what is the directionality of the forces and all, but the force diagram that it gave was completely incorrect. So if you wait to take the representations into account, the diagrams into account, almost each and every response of the 16 AI responses were conceptually incorrect. So on the contrary, every student constructed a diagram and frequently referred to it. However, only 3 AI solutions generated diagrams without explicit prompt. Even the ones which accompanied diagrams were unsophisticated or inaccurate. That's what I just mentioned. So AI platforms usually don't have the natural tendency to explain a concept using a diagram. On the contrary, students often make sense of some things using gestures or diagrams. So okay, let me speak that in implications. Okay, so now let's discuss about what these results mean. So surprisingly, at the same time, there was one more paper that got published in chemistry education research, who were also simultaneously looking at the features of mechanistic reasoning, but while explaining the mechanisms of chemical reactions, like how a particular reaction can give rise to a particular product and what is the underlying mechanism that follows. They observed that GPT 3.5 generates very sophisticated mechanistic accounts, but with lesser accuracy of correctness. Again, the features are there, all the codes are being exhibited, but the accuracy of the AI responses is just 28%. So also observed AI to evidence entities. Our findings align except for accuracy. I mean, if you wait to just take out the diagrams and just focus on the solutions, we almost had 100% accuracy in the solutions. But we too observed that AI systems were very good in evidencing the features of mechanistic reasoning or sense making. In another study, again in chemical education, chemistry education research, at almost 6 months before, they analyzed similar, like student and AI generated mechanistic explanations. The authors observed AI responses to lacking these processes, explicit emphasis on how the chemical reactions are occurring in AI responses. In fact, our results contradict these results, clearly showing that as we go through the evolution of these AI platforms, you can expect more and much more sophisticated response from AI. I mean, the whole idea that AI can be incorrect in a given context, that probability is going to go less and less as the AI platforms evolve. So this is something that we can observe. So this also brings this question of whether how an AI responds to a mechanistic question, is it context or discipline dependent? If you wait to ask a biology question or if you wait to ask an interdisciplinary question, will it evidence the mechanistic reasoning features in the same way as a purely disciplinary question? So that's something that there is this uncertainty in making these arguments. So now let's slowly talk about implications. So what are the implications of these findings? One is AI is particularly effective at conveying through right vocabulary and structure. So physics communication is very important. And the communication is intrinsically sometimes linked to rubric. Because when we grade physics problems, we have to look at the rubrics as whether there is a diagram mentioned, whether that force is mentioned, or whether certain features are mentioned or not. So AI is pretty good at conveying these solutions through right vocabulary and structure. Beneficial for introductory students in structuring and communicating solutions. So one of the things that we often do not explicitly talk about in classrooms is about how to communicate the written solutions, particularly when the answer matters. So if AI solutions can be very good at implicitly communicating how to structure and tell a particular idea, how to communicate a scientific written solution to other audience. So activities centered on solving real world problems and comparing them with AI solutions can help students communicate using relevant vocabulary and structure. And this is particularly true so for people whose primary language is not in English. So this is also one of the added layer to the complexity. I mean, I am from India, and at some point people start learning science in English. So before that they just learn science in their own language. And often this is also a problem, like how do you communicate, what is the right vocabulary to call out, and at what instance the right word should be used. And AI is pretty good at this. Like you solve a particular solution and then check how AI solution is talking about. It can implicitly and explicitly tell you how to communicate this idea. So nudging students to identify the appropriate target system, relevant entities, and their activities can lead to enhanced learning. So this argument we are making because the idea is now to train a large language model using the textbook that we are referring in the classrooms. And we are trying to, in fact, train the LLM using these features. If any AI generated if student generated solutions is missing a particular entity or processes, ask AI platforms to reflect on it, push students to articulate it clearly, and then start resolving the problem. So this is along something along the lines of adaptive assessment. So this is one of the interesting thing. So the reason why we observed large language models to behave weirdly with representations in physics is because these large language models are just trained to reflect their training data. So what happens is they present a solution and they just call out the representation that was used. But in physics, that's not how students use it. So students first construct a representation, they solve again, they go back to representation, modify something and come back. So one of the things interesting that we would like to check is, like, if students consistently started using AI platforms to solve physics problems, whether that will hinder their representational fluency or the habit of effectively navigating between multiple representations. So there is a significant difference in the correctness of solutions between the two evolving models. That is also a cause for concern. So that's actually an educational divide problem. The more robust AI model you have, there are very inherent abilities or inherent strengths that you will have when compared with freely accessible AI models. So that's also needs to be taken into account. So this paper, in fact, we have published all the arguments in detail, and it got published just few months before. So we also have how students is making these gestures while solving the problem, why it is right or so, and what is really happening. So you can in fact find all the detailed qualitative analysis of what students said, what AI said, and how these markers were identified and all. So yeah, I think that's the big picture. Thank you so much for listening, and I hope I did not cruise through fast through the presentation. And here are all the references that you can have.
Did you do a reverse search on the image or the diagram, that goofy diagram that it produced?
Reverse search.
I'm wondering where that diagram, like, is it taking pieces of other diagrams, or how was that diagram produced with the person that's backwards? I was wondering if you did a reverse.
Yes.
Just see if some of those pieces came from somewhere and why it came up with that particular diagram.
So what I tried with different prompts. So the one of the limitation is that we use zero-shot approach. We in fact gave the problem statement as we gave. So what I tried explaining was how the person was, what is gravitron on how the person is positioned, will it in fact generate a different image. So surprisingly, it generated correct images, but which did not have this one. Like it was just an arrow images. You have a dot, which is the person, which is at the center of mass, and then you have the gravity down. So what happens is conceptual accuracy increases, and if there is an ambiguity, AI has the tendency to merge images. It takes part of the image from one problem and part of the image on the problem. That's why there is a lot of inconsistency in that. Yeah. And if you become more specific, more elaborate, and more descriptive in nature, then it produces the right representations. But the sophistication also slightly decreases.
I mean, it was also interesting that it was sort of like a, you know, from the 1800s or early 90s. You know, I mean, the style of that diagram that it created. I mean, I guess I would have expected something akin to a free body diagram, maybe a little more elaborate. But you know, when it had those features, I just wondered if it was pulling from, you know, like from physics.
Yes.
Physics books. Yes. And the other question I just had, I didn't catch with the students, like, I think his name was Joseph or Jacob, are those students doing those problems after they have already studied that content and it's sort of...
Yes.
Okay.
Yes.
So that when you had scaffolds, you compared the responses of the scaffolded questions between the student and AI. Mm-hmm. Those students weren't in the process of learning.
No, this we intentionally did at the end of the semester, so that students can bring in as many ideas as possible when they are trying to solve this problem. So all these interviews were collected at the end of the semester, when they had learnt almost all relevant ideas.
So I had a question about the input. So the ChatGPT window, if you need to put in like mathematical notation, and then in the output, if it needs to output mathematical notation, how does that work physically?
So, so it can be done in two to three different ways. One is that you can directly go to LaTeX, which AI platform is pretty good at reading that language.
Okay.
So you put the LaTeX code and then check how the AI platform responds. This is the conventional way in which researchers have explored with mathematical expressions. The other way is to run the LaTeX code, and it produces a PDF format of the problem with all the algebraic numerator. And you just copy and paste it, because it understands the LaTeX thing and it also understands the LaTeX output. So that's the second way to do it. So we did the second way.
I just need the educational implications, because if you want students to use it, then they also have to learn how to do that, right?
So you can in fact, so you can in fact ask the reverse way. Right. So you can ask AI to generate a LaTeX version of this, and you then tweak it and then you feed it back.
Can it, along those lines, can you also just have people write out the equations and take a picture, and then will it be able to sort of understand what those equations are, handwritten equations?
Yeah, so there was in fact a platform that was developed precisely for this. So what it did was, I mean, the reason I know is an entire study was conducted based on this. So they used this technology to check how students were solving thermodynamics problems and to what extent AI was very good at measuring the accuracy. So what AI does is that it takes the image format, it converts into LaTeX. So that LaTeX, it inherently checks consistency, whether there is any problem with the code and the response and all. And that instead of going through the image, it reads the LaTeX code and then it grades student solution. So this was before this vision capable chatbots were there. So even the earliest GPT version is pretty good at LaTeX and programming.
So I have a question that's somewhat related to what Wayne asked. There are kind of some understood effective practices for prompting AI. So the more specific you are, or the more, if you can point it in certain directions. So when you submitted your your prompts, the questions,
Mm-hmm.
were they refined in any way to align with effective ways to communicate with ChatGPT or AI in general, or did you simply use the way it would have been asked on a final exam or something like that?
So we intentionally use that zero-shot approach
Okay.
because we did not want the discrepancy between how we interact with the platforms and how we interact with students. The problem was given in the same way as we had given to students without providing any background. And to ensure that, we in fact started a new API for that. So the AI is pretty good at actually with drawing inferences from your previous chats when generating solutions. So we in fact took a new account, we had zero background in it, and then we started prompting.
Have you ever responded to one of their responses to let it know that it's incorrect?
No, because I was very careful with the data. But we have played this with mathematics. We have played this with different physics and mathematics problems that we solve. So there is this literature, I have one of that is the prompting technique called self-consistency. So when you iteratively run the same prompt and ask AI to recheck whether you are consistent or not, third or fourth time there is a huge probability that AI will get you the right answer. And it will also recognize that there was some sort of mistakes that it did. And you can also do other things. Like what you can do is, GPT 3.5 was very bad at maths, like doing integration, differentiations and all. So what you can do is you can in fact outsource that to MATLAB or Mathematica. So there is an inherent thing. So what you do is that activity you outsource is to Mathematica. Mathematica does that churning and gives you just the result. That's how you increase the accuracy. Yes.
First of all, thank you so much for your presentation. It is wonderful. Nowadays, we have been using AI tools somehow, whether that is less or more. But I understand that AI tools, they take our data.
Yeah.
So as a researcher of AI and physics, what advice do you want to provide regarding the data privacy?
This is in fact a very tricky question. The more I think about it, the more I realize that the data privacy is already violated to a very large extent the moment you connect, you sign in. And see, the problem is that sometimes, for example, I have used my Gmail account to sign in with ChatGPT. So that intrinsically violates a lot of things. So your Google credentials are already shared with OpenAI. But when it comes to protecting students' privacy, so this is something that if we wait to design any activity and if we want to ensure that students' privacy is taken into account, what I usually prefer is that go to those platforms which university provides, for example, Copilot. I often say that don't do any other activity with your personal accounts, go to Copilot, because the chances of your data being secure with university sponsored is very high. The data remains local. Yes.
Yeah, can I, since you mentioned about the zero-shot approach, can I just say more about that slide?
Yeah.
Thank you.
Oh, sorry. I'm not.
Yeah, so I see there is an n equals to 8 on the left side. I know that's the student's number. And then on the right side, you said zero-shot approach, n equals to 8. What does that 8 mean?
So we collected 8 responses from GPT 3.5 and 4.0.
So you put a prompt 8 times to see what
Yes,
comes out?
yes. So simultaneously starting a new chat.
Yeah. I'm thinking, have you tried other kind of AI tools, other than ChatGPT, like Gemini? Like that?
No, there are 2 reasons for it. One, a recent paper published that GPT was almost better when compared with any other platform. And second, we also know that ChatGPT was something that people were using more as compared with any other AI platform. So that's why we in fact did not bother to investigate that aspect of research question. I mean, we are also thinking to what extent does it make any difference.
That
Nope.
makes sense.
Yeah.
Can you just explain more about the zero-shot approach?
So there are different prompting techniques, like there is this zero shot, one shot, and multiple shot approaches and all. So in zero shot approaches, you just interact with AI platform as if you take a lot of things for granted and as if you interact with a person. Right? I mean, for example, if I were to go and speak with a physics student who is taking an introductory course, that at the end of the semester, there are a lot of things that I make assumptions about that student. Like that student knows what the Newton's laws are, what momentum is and all. So I directly pose that question. Okay, if this is how it happens, what would be the answer? That's what is called a zero shot approach. You prompt it assuming that the AI platform knows all the context behind it. In other prompting things, what you do is you provide a detailed context. Okay, the discussion from henceforth is about physics, particularly introductory physics pertaining to force and motion, and then you present a solution and what you expect from it. So the way you prompt, there is a huge difference between multiple things. And there is also other shots where you in fact associate a role to the platform. Okay, now start behaving like an introductory physics instructor. Your job is to provide a coherent solution with as many minimum mistakes as possible for this given problem. So there are various, prescriptive features for every prompting strategy that has been described. And zero shot is the least, complicated thing. You just make all the assumptions and give it.
Thank you.
All right, I think we'll wrap up for now. Well, thank you very much.
Thank you.
Yeah, please.